So this is what we're going to try to do today. These are all Alex company. So we're going to identify common acids and bases by their chemical formula. We're also going to identify if it's an acid or a base. We're going to identify what a Bronsted-Lowry acid and base is, and then we're going to also figure out what this conjugate acid or base means. So I have an activity. Let me make sure I got the right one this time. So I want you to take these and organize them into 3 groups. So figure out what's similar, what's different. Go ahead. There's not a wrong way to do this. Go ahead and organize these. Go ahead and organize them into 3 different groups. And then we'll talk about how each of us organize them.
Oh, no.
So again, there's lots of ways to do this. We are just trying to categorize them into 3 groups.
Non-medical, that's what I'm thinking about. That would be so cool. It's like oxygen. So yeah. Well, yeah.
All right, did you guys figure that out or categorize them? You got them in 3 groups? You need a minute?
Oh, 3 groups?
Yeah, 3 groups.
Oh.
Okay, do you want to tell us how do you group them?
These ones are ionic.
Ionic?
And these are sorry, valent, and these ones are constant.
Okay.
It's
Okay, so ionic, molecular, and acids or bases. Okay. Okay, how did you guys group yours?
Those are ionic.
Okay, ionic,
And then
and then the other ones. Okay, ionic and the other ones. How did you guys group yours?
these are bases.
Okay.
Those two look like they would.
Okay, and just like they look similar. Okay. Hey. How about Isaac and Cooper? How did you guys group yours?
so these are hydrogen bonding.
Okay, hydrogen bonding. Okay,
These are ionic.
ionic.
These are
Okay, all right. So some of the categories we learned already.
we are ionic.
Okay, all right. Okay, very good. So we have lots of different ways that we can organize the compounds. This is one other way that we can organize them. We can categorize them as acids, bases, and ionic, and I think some of us did that. So again, there's lots of ways we can categorize these. If we categorize them by acids, bases, and ionic, then these are the acids, these are the bases, and these ones are the ionic compounds in our groups. So look at those for a minute. Oh, also, do you have the acids and bases paper? I handed this out during last quarter. These are the acids and bases that you will have to know. for the test. You have to memorize them or put them on your note card. You have this paper. Okay, I can make more. I have 2 more, or I can make more if you need. But on this paper, these are the ones that Alex is going to expect you to memorize. So we need to be able to recognize these as acids, these ones as bases, and then we can recognize these aren't either. Those are just ionic compounds. So what do all of the acids have in common?
Don't start with H except the last
Okay, they all start with H,
is common.
except this one. This is acetic acid. This is vinegar. If you dilute this, this is vinegar. And that's, if you look on your paper, can you put it in the dumpster outside?
Where's the dumpster?
In the parking lot over there. Okay, thank you. What were we doing? I don't remember. So these are acids. Oh, acetic acid is the one weak acid that you have to memorize. So you need to memorize that. There's a lot of different weak acids, but acetic acid or vinegar is one that you have to memorize. And it has a few different ways to represent the chemical. These are bases, so these have something in common. If something has OH, generally it is a base. This also has OH, so that's a little bit confusing. This one is an organic acid, vinegar. These are bases, they give off OH in solution. So again, these are also ionic. They're an inorganic base, an ionic base. This is ammonia. This is something that we've already had to memorize. This is a weak base. So that on your list, ammonia is the weak base that you need to remember. So it's kind of like our weird exception.
So the 2 weak bases are.
So
That's a NH.
NH3 is a weak base.
And then the.
Vinegar is a weak acid. Yep, acetic acid. Acetic acid. Okay, and then these are just some ionic compounds we have. Mg plus, 2 plus, F minus, NH4 plus, Cl minus. So that we just have to recognize those as ionic compounds. Okay. All right, so there's 2 different definitions of acids and bases. So one is this Arrhenius acid. If you took chemistry last year, we talked mostly about this type of acid. This is where if you add something to water, we get out a proton and then the counter ion. So this is an acid because we get out H plus. Okay. So this is this person defined an acid as giving off a hydrogen ion or H plus. An Arrhenius base contains hydroxide. So this is one definition. And this is the definition we talked about in my class last year. And this is pretty helpful. If you can see that we have hydrogen at the beginning, it's going to break off and form a hydrogen ion and an anion. And then we can also see sodium hydroxide from our last chapter. We can see that we have sodium ion, we have hydroxides, those will split off in solution. And this hydroxide is what makes it a base. So this is still a helpful definition, but there's one more definition that we're going to stick more with. All right, the other definition is called the Bronsted-Lowry acids and bases. And this is where we're just looking at where are the hydrogen ions going. So we also call this a proton, this hydrogen ion. If we look at our periodic table, we remember back to probably quarter one, where we're talking about what makes up an atom. We have protons and we have electrons. If we give away an electron, so hydrogen has one proton, one electron. If we give away the electron, all that's left is the proton. So often chemists call the H+ ion, they call that a proton. And so I will probably also do that. So if I'm talking about a proton, I just mean H+. Okay, those are interchangeable. So Bronsted-Lowry acid is a proton. Bronsted-Lowry base is a proton acceptor, donor and acceptor. So we just have to figure out in the chemical equation what is giving up the proton or the H+, and what is accepting the H+. So if it's giving away the H+, so if we look here, we have HCl, and then over here it ends up as Cl-. So H was given up by HCl. So this is our Bronsted acid. Thank you.
Yeah.
And then this one, water, goes from just water to hydronium. So it's accepting the hydrogen ion. And so this water here is the Bronsted-Lowry base. So that's the other definition. This is the more complete definition of an acid and a base. So we're just watching where are those protons going. So again, if we're giving away the H+, that's acid. If we're getting the H+, that's the base. So that's something that you want to keep straight. That might be something that I would put on my note card for the test, just to make sure that I remember that. There's also an Alex topic just like this, where you have to, it'll highlight one of these and it'll say, is this one the acid or the base? Well, if it's giving away the hydrogen, it's the acid. If this one's highlighted, then it's the base, because it's getting the proton, the hydrogen. Okay, so here are some common ones. Again, the ones that you will for sure have to memorize or write on your note card or on this sheet. And if you need another one, I will also try to remember to post that on Canvas. Let me write that down so I don't forget. So you can look at that. All right, so we notice with these ones, we have all these hydrogens that we can donate. So this sulfuric acid has 2 hydrogen ions that it can give away. So it's a kind of special type of acid we'll talk about in a minute. And then acetic acid, some of these hydrogens are not acidic. These are called the non-acidic protons. This is going to be acidic. It can come off of the rest of the molecule. If you take organic chemistry, you will talk about all of these organic molecules and all the hydrogens and how easy it is to pull them off based on their structure. So. Okay, so again, these are on your sheet. There's a few more on your sheet also, so just watch out for those. Protic, so again, this H+ is a proton. So the protic number is the number of protons an acid can give us. So monoprotic, we have a lot of monoprotic acids that we will have to memorize. Those just give off 1 hydrogen. Okay. A diprotic acid has 2 protons that it can give off. So this is sulfuric acid. Sulfuric acid can give 2 protons. This one is phosphoric acid. That is not on your list, so I'll double check and make sure you don't have to memorize that one. But this one's triprotic. It has 3 hydrogens that are really easy for it to just give away in solution. Okay. The other thing that this is pointing out is that we can have our hydrogen be on a neutral acid. We can have it be on a positive acid. So hydronium can give up a hydrogen. Or This has already given up one hydrogen. We now have a second hydrogen we can give off. So there's lots of different types of acids. We can have a negative, positive, or neutral charge. And we won't talk about titration today, but this is really important for titration because you need to know how many moles of hydrogen you have. So this will give you 3 moles of hydrogen for 1 mole of phosphoric acid. This one will give you 2 moles for the moles of acid. We'll talk about that later, but it's important to know what this monoprotic, diprotic, and triprotic means. Phil, sorry.
So, stupid question, but when a base accepts a proton, is it basically just acid?
Yeah.
Okay.
Yeah, good question. Yeah, that's good. That's good thinking. Other questions or thoughts while we're writing? Okay, so a Brown-Sedlowry base is a proton acceptor. To be a proton acceptor, you have to have a lone pair. So anything with a lone pair can be a Brown-Sedlowry base. So we're going to look at this example. So this is our weak base, ammonia. Ammonia has a lone pair on that nitrogen, so that has a full octet. If we're looking at this, what's happening is water is going to give away, water's going to split into 2 pieces. It's going to split into H plus, and it's going to split into OH minus. Okay, so if we combine these, it'll go back to water. So this H plus is our acid part, and it's going to connect with the lone pair. So now, notice H plus is positive, so it makes the ammonia positive. So we have to watch our charges. So this side started as a 0 charge, so this side must be a 0 charge. So we have our minus and our plus, that gives us a 0 charge. So this is now a positive charge because it got the positive hydrogen ion, and the hydroxide is negative, and it comes over here. So here, because this is accepting a hydrogen, that's the base. Because water here is getting rid of the hydrogen, it's the acid. So for something to be a Brown-Sedlowry base, it has to have this lone pair. So the lone pair, remember we have this electron cloud. That electron cloud is what's going to bond to this hydrogen. So that lone pair on the nitrogen can accept that proton. Okay, other thoughts, questions? I sometimes can't tell if you're still writing or not. Okay, so here are some Brown-Sedlowry bases. So ammonia is one that we're going to have to memorize. Water can act as a base or an acid. So here it's listed as the base. And then these all have OH. So those are going to be easy to recognize. If it has OH and it's an ionic compound, if it's this metal salt, if it's a metal salt and it has OH, then it's going to be a base. And these are on your sheet, but also we should be able to name these because we have the metal and we have hydroxide. Okay. All right, this is kind of an interesting word, amphoteric. So amphoteric just means it can be an acid or a base. So we said this already. Water can be a base, so it can accept a proton. That's what makes it a base. Or water can be an acid. We can pull off a proton or a hydrogen from water. And just like Phil was saying, if we have a base and we add a proton, it really becomes an acid. So if we went back, if we drew the arrow backwards, if we go this way, then water is acting as a base. If we're going this way, then we can have hydronium. This is hydronium, can act as an acid. So that's why this is the conjugate acid. So we always have a conjugate base and acid pair. So here, water is acting as an acid. We're getting rid of a hydrogen. Now we have hydroxide. This is the conjugate base, because if we go backwards, then hydroxide will be, if we add a proton, then it's going to act as an acid, or a base, excuse me. We're adding it, so it's going to be acting as a base. So we always have the conjugate acid-base pair. So notice that these always will differ by 1 H plus. So from here to here, oh, my mouse is going on. From our water to our conjugate acid, we added an H plus. So we have to keep our charges balanced. From here to here, we got rid of an H plus, so we got a negative charge and we lost the hydrogen. Okay, and this is just a summary. So we can identify the acid, and sometimes we do use this form. We use HA as our acid. So the hydrogen is leaving our A. We end up with the conjugate base. And here we have our base that has a lone pair. So the base is what's going to end up with our hydrogen. Okay, so that's kind of our shorthand. All right, and so let's go over the conjugate base one more time. So the conjugate acid and base. So if we have our acid over here, the acid is what's giving away the hydrogen. This is our conjugate base. That's what we're end up with after the proton leaves the acid. The base ends up getting the proton, and so that's our conjugate acid. So the base always goes with the conjugate acid. The acid always goes with the conjugate base. So that there's always this pair going on. Okay. And if we ran the reaction in the reverse direction, then that would be our acid, that would be our conjugate base, this would be our base, this would be our conjugate acid.
So conjugate is always used for the resulting product.
Yeah, yeah, good. The conjugate is always the products. Good. Okay, I think this is also important. So we have, in this equation, we have HBr and Br minus. So we have our acid and our conjugate base. And then here we also have water is gaining the hydrogen, so it's our base. And hydronium, H3O plus, is our conjugate acid. So if we look at these equations, the charge has to balance. So this starts as a 0 charge on this side. So this side must also be a zero charge. So we have negative plus 1 positive, that gives us a 0. So the pieces aren't neutral, but they add up to something that's neutral. And then we also have to make sure that our hydrogen's balanced. So our hydrogen, H plus, just moved from the acid to the base. Okay. And the other thing to watch out for is the only difference between the acid and the base is this H plus. Okay. So this is neutral. We lost a plus charge, so we have to get a negative on our conjugate base. We also lost the hydrogen, so we better not show the hydrogen. And then this ends up with a hydrogen plus. So it gets another hydrogen, and it gets the positive charge from the hydrogen. So the hydrogen is moving, but also the positive charge is moving with the hydrogen. Does that make sense? Okay. All right. I think what's next, we're going to do another activity with these little pieces of paper. So these ones, you're going to match the conjugate acid and the conjugate base. So again, they're going to differ by 1 hydrogen and a positive charge. So match the pairs together. Oh yeah, I don't know that. I can drink you. Oh, sorry. Yes. Yeah. Let's make them bigger. Okay, we talked about that. Okay, this is just summarizing when you add a charge, you lose a charge. We talked about. So you're matching the conjugate base and the conjugate acid together. So they should differ by a positive charge and a hydrogen. And there's some examples up here. This is on the all right, how do you guys do? You thought we should pay attention. So where are the pairs? These are pairs? Oh, okay. So we're finding an acid-base conjugate pairs. So they're going to differ by a hydrogen ion and a plus charge. That's the only difference. So like one to the next one, we're either taking or adding hydrogen.
Oh.
Okay, so from here to here, you're gaining hydrogen. Yes, so these are yes, good. So these are a pair because from here to here, you're losing hydrogen from here to here. Good. All right, you guys doing okay? Okay, yeah, that's good. You're doing okay? You got it? Good. Okay, you got it? Looks good. Okay, good. So this is a little bit confusing. Alex is going to make you write out the formula. So you're just doing the same thing. You're going to, in your head, add or take away a hydrogen, or you can write it out. So you did that. So these are, and again, we can say this is our base and this is our conjugate acid, or we can start with our acid and go to our conjugate base. So I'm just writing, these ones are the acids and just these are the bases. It depends on which direction we're going in the formula. Okay, but I think you guys all got that. Okay, very good. We have like just under 20 minutes. The bell has been ringing like 2 minutes early. We get out at the 50, so we have a little bit of time left. So go ahead, the rest of the class period, either work on the chapter 9 Alex, or work on lab 10, or if you're all done, you're all caught up, go ahead and work on the pre-lab for lab 12. Yeah.